I want to try to give you a little bit more understanding of why trigonometric ratios um, work. If you remember on the previous video, I said that or I implied in a certain sense that for any given right triangle, for a right triangle of any size uh, that has a given angle, that the ratios, the trigonometric ratios, are going to remain constant. They're going to remain the same. Okay, let me see if I can say that again. So for any right triangle with a given angle measurement, like we see here, we've got we've got triangle ABC, triangle AA prime D, and triangle AB prime E, three triangles here. Those triangles each have an angle of 30 degrees. So their trigonometric ratios are going to be constant, or they're going to remain the same. For example, with the tangent ratio, I'm comparing all these triangles are similar. This is all based on similar triangles. Okay, these three triangles, ABC, AA prime D, and AB prime E, they're similar triangles because they have two angles. They have two angles that are the same, two corresponding angles that are congruent. Okay, so see, these are similar triangles, and that's what the trigonometric ratios are based on. I'll try to make more sense of that in a little bit. But here's an example. I've got three triangles that each have a 30-degree angle. Notice that the tangent ratios, for example, that's opposite over adjacent. So for this triangle, it's BC over AB. For the other one, it's AD over AA prime. Notice their ratios are equal. Okay, the tangent ratios. Okay, and it doesn't matter what size those triangles are. All right, as long as that angle stays fixed. Notice these side lengths are changing, but my trig ratios are not, as long as that angle stays fixed. Okay, so with similar triangles with a given angle, those ratios are going to remain the same, and that allows us to solve for unknown side lengths using these ratios. Same thing with sine and cosine. Okay, so I got 30-degree triangles here, and notice the ratios of those triangles are all the same. Sine is opposite over hypotenuse. So for example, I've got BC over AC. And again, doesn't matter what size the triangle is, those ratios are going to stay constant. Okay? And then there's a cosine ratio, same thing. All right? So what people have done, if I'm going to look at a table. This is in the back of your book. They've categorized, they've recorded all the ratio values for a given right triangle. So here's a right triangle with a 1-degree angle. So you got a 90-degree angle, a 1-degree angle, and an 89-degree angle. And these are the ratios of those. These are the values of those ratios. They're in decimal form. Those are the values. Okay. So let's say, for example, I'm looking for, I've got a right triangle with a 20-degree angle. All right, and I want to find I've got the 20-degree angle. I want to find one of the side lengths. Okay, so I could use sine. All right, and so the sine ratio is to 0.342. Okay, so that 0.342 has to equal, x. If I'm looking for the opposite side, x over the hypotenuse, and I can solve for one of those. Okay, that wasn't a very good explanation there without a visual. But if you go down here, notice before we had a 30-degree angle. Okay, remember the ratio. These are the same ratios that we saw that I showed you earlier. Okay, so we'll see how we can apply those um, to solve for unknowns. All right. For example, with this problem here, I'm looking for x, the length of this leg. I have an acute angle 61 degrees given. So the sine, let's see, what are we solving here for? So that we've got an adjacent leg, or we've got this leg here, and this. So that would be, we could use tangent here. So the tangent of 61 degrees has to equal opposite over adjacent. So that's 22 over x. Okay, so the tangent of 61 is some value. If you go back to your table, let's see if I have it on here. The tangent of 61 is 1.8040. So I'm just gonna estimate that at 1.8. So 1.8 is equal to 22 over x, and I want to solve for x. Get that unknown, and that's going to give me this leg length. So the way that I'm going to do it is I'm going to try to get, this is 1 over x. I want to get x, so I'm going to multiply this side by x and this side by x. Okay, so these x's cancel out, and so what I have is 1.x is equal to what do we have? 22. So then when I divide 22 by 1.8, I get 12.2 repeating. Okay. We'll see later how we can use our calculator instead of this table. All right, so for this one, let's say I'm solving for A. I've got this 48-degree angle. I could use this angle here too, but I'm solving it for A. So from this 48-degree angle, I want the hypotenuse. I have a leg here. So that with this angle, I've got the adjacent leg, and I need the hypotenuse. So that's cosine. Cosine is adjacent over hypotenuse. So the cosine of 48 has to equal adjacent, which is 10, over A, the hypotenuse. So if you remember from the previous problem, if I multiply both sides by A, I've got A times the cosine of 48 degrees. That has to equal 10. Okay, so I multiplied both sides by A to get rid of this 1 over A. Okay, then again, the cosine of 48 has a value. Okay, and that value is, let's see if I've got it up here. That value is what? Cosine, 0.6691. So I'm going to use 0.67. Okay, so 0.67. So I've got A times 0.67 is equal to 10. So to get A by itself, I'm going to divide 10 by 0.67. And I've got 14.9 approximately. A is approximately 14.9. Okay. So those are using the trig ratios. On the next video, I'm going to show you how to use the calculator and make it a little bit more simple.